Okay, then we go to the next speaker, which is going to be Julia. Julia, if you want, you can share your screen.
Yeah, give me a sec. Okay, is it visible?
It is, it is.
Okay, perfect.
Okay, so are you ready, Julia? Can I introduce you?
Sure.
Then we have our second speaker of the day, who's going to be Julia Ramos Gonzalez, and her talk is going to be about bicategorical presentations of étendues. And Julia, take the stage whenever you feel ready.
Okay, thank you very much. I would like to start by thanking the organizers for inviting me. It is a great honor to be part of Ithaca Fest. And with two apologies. First of all, if Enrico said that the quality of his talk will be not good enough, of course, then I mean, I cannot have comparisons here, so I'm sorry. And then I would like also to apologize to Andrea, because unfortunately I have to leave after my talk, so I will be missing his talk. But if it's recorded, I will definitely watch it afterwards. So this said, I'm going to indeed talk about bicategorical presentations of étendues, and this is a joint work still in progress, by the way, with Darien de Wolf and Dorette Pronk. So let me get started with a recall on what étendues are. So a grothendieck topos A is called an étendue if there's an object on this topos such that the map to the terminal object is an epimorphism. And then the slice topos over this object is localic, meaning that it is equivalent to the sheaves over a locale. And so the slogan would be that étendues are the grothendieck topoi that locally look like a locale, but may not be globally a locale, so a category of sheaves over a locale. And so we have a few examples which are well known. The very much more common is G sets, in which our object that we can choose to see that the definition is satisfied is G itself. We can also, this is an example by Lovir, so sets with an endomorphism fixed, in which you can take as this object the natural numbers with the successor function. From SGA, we can take, for example, G equivariant sheaves. So basically it's a topological space with an action of a discrete group G. And so we take sheaves that are compatible with this G action. And if we take the product of G itself with the terminal object, it gives us an étendue, I mean, the conditions to satisfy the definition. And also we have categories of pre-sheaves with over categories, small category C, in which all maps, all morphisms are actually monic. And in there we can take the co-product inside the pre-sheaves of all the representables, if you want, to all the objects in C, and this will make the definition work. So these are our objects, and there are several ways of presenting these objects. Let me start recalling localic groupoids. So localic groupoids are internal groupoids in the category of topological spaces. Well, in this case of locales. Let me for a moment. And we have presentations. Let me start with objects. So the classifying topos of an étal localic groupoid, étal meaning that the domain and codomain morphisms are actually étal maps, is an étendue. And we have also the reverse direction that we can find SGA4 or in Joyal-Tierney. I must say in SGA4, the definition of étendue is not over locales, it's done spatially. So it says that locally our topos is a space, really a topological space. And afterwards, the more standard definition that Lovir extended was, okay, let's consider locales. And so in SGA, this was done for spaces, and then Joyal and Tierney proved it, showed it for localic case. So any étendue can be recovered on this manner. So in This étale locale groupoids gives us good presentations of étendues, but this is at the level of objects. What happens one categorically when we have this result by Ike-Murdek that says, well, there is a functor which is taking at the level of objects the classifying topos that goes from the category of étale groupoids to the category of étendues with geometric morphisms that induces an equivalent when we invert the essential equivalences. And this recovers the category of étendues with morphisms, the geometric morphisms, as a category of fractions in the sense of Gabriel-Sisman of étale groupoids. And we can push this if we are interested in étendues not only as a one category, but a two category in which you consider natural transformation between the left adjoints on the geometric morphisms. Then we have for a spatial étendues, so locally a topological space, we have this result by Doret-Pronk, and that this functor can be actually extended to a bifunctor, in which from étale groupoids to étendues with the correct notion of two cells, I won't enter into this, that induces a bi-equivalence between the T1 étale groupoids, so the one in which we are inside T1, so internal to T1 locales, to topological spaces, to the T1 étendues, which are the ones that when we take this sliced opposite sheaves over a T1 topological space. And in here, we are inverting the same morphisms. And this is using the theory of bicategories of fractions that Doret, in this very same paper in which she proved this result, introduced, generalizing that of Gabriel-Sisman for one category. So in here, the picture is very complete. We recover étendues, well, T1 étendues, but we recover them in a two categorical way using localic groupoids. Let's move to other presentations. So we have presentations also in terms of sites with only monic maps. So a small category, we say it's left cancellative if all its morphisms are monic. And why this terminology? Basically because a left cancellative category with one object is a left cancellative monoids. So we think of these guys as monoids with several objects, left cancellative monoids with several objects. And we have presentation at the level of objects. Rosenthal proved that the topos of sheaves on a left cancellative Grothendieck site, so we have a Grothendieck site whose a small category, underlying category, forgetting the topology, is a site with only monic maps. And on the other way, we have the result by Koch and Murdek that proved that any étendue can be recovered in such a manner. So we have these nice presentations at the level of objects. And before I move to what happens in higher structures, let's go to revise the third type of presentation that will be showing up today, which is Ehresmann sites. Well, we define an ordered groupoid to be an internal groupoid in the category of posets. Imposing one extra condition is that the domain is a fibration, which implies immediately that the codomain is also a fibration. And Doret and Darien, the Wolf, they proved that we can actually, they gave this very nice graphical interpretation using double categories as follows. So we can picture the ordered groupoids as double categories in which we see that we put the objects. So the objects in G0, which is our post set of objects, are the objects of the double category. Vertically, we put the partial order in G0 in the post set of objects. Horizontally, we have the objects in G1, which are the morphisms, so the objects in the post set of morphisms. And we have a two cell if and only if this F is less or equal than F prime in the order in G1. And with this picture, which forms a double category, the vibration property translates to the following. And that is that any diagram, which is just a left bottom corner, can be completed uniquely to a 2-cell. And because it is unique, we denote the top arrow, the restriction of F to the object A prime. So we have these ordered groupoids, which we can see them. I mean, we can work with them as double categories this way, and we can put topological information on them. And so let me define it. An Ehresmann topology on an ordered groupoid is an assignment for every A in my groupoid of a collection of vertical sieves. Vertical sieves are basically just downclosed subsets of the bigger downclosed subset that contains my object. And we impose 3 axioms, which are very, very similar to the axioms of a Grothendieck topology, but with this vertical information. First of all, that the biggest sieve is actually covering. Then we have that for every sieve covering in my topology and every such diagram, the vertical sieve, or ideal if you want, which is this pullback, is also covering. This, I won't enter into details, is basically all the arrows on top of B vertically, such that when I fill in that 2-cell, that I have this unique 2-cell, then what appears on the right is inside S. So we have the compatibility with pullbacks, as in Grothendieck topologies, and the very same local characters. So for any 2 sieves, S being covering, R being just an arbitrary sieve, then if I pull back R along morphisms whose vertical part is in my covering, and this belongs always to the topology, then R initially belongs to the topology. So this is an Ehresmann topology, and what we have is now what's called an Ehresmann site, which is an ordered groupoid endowed with this information. And let me define also pre-sheaves and sheaves, which are in a very similar fashion to the Grothendieck part of the story. A pre-sheaf is just a double functor in which we reverse the direction of both vertical and horizontal arrows, taking values in Q set, where this is just the 2 category in which both horizontal and vertical arrows are just maps of sets and 2 cells are just the commutative diagrams. And what is a sheaf? A sheaf is just a pre-sheaf, such that for every object and every covering sieve of that object, and given every compatible family, so elements in F of AI, where my AIs are the elements in my covering, then there's a unique S clue in the family. I won't enter into the compatibility condition, but if you sit down and think what should this be, it is what you would expect. And so this gives us another presentation of étendues. Lawson and Steinberg proved that the category of sheaves in this sense that we just introduced on an Ehresmann site is an étendue. And sorry, okay, so there was some comment. And we have also the reversed that was proved by Darien, De Wolf, and Dorette Pronk, which was that any étendue can be recovered in such a way. So we also have nice presentation at the level of objects. What happens for bicategories and for 1 categories? Well, we have the following picture. Let's start with left cancellative with both, because they can be very nicely related at the same time. So I have ordered groupoids, I have left cancellative categories, and then Lawson proved and constructed 2 functors going in both directions, where you restrict ordered groupoids to this called max order groupoids. Basically, it's a small technical condition saying that every object is has a unique maximal element, if you want, above it. And so he constructed these 2 functors. And if when putting the topology information, so Ehresmann site and Grothendieck site, what you obtain is that this functor, the C1, actually commutes with taking shifts. So I can take an Eresman site, which is max, compute these shifts, or go to left cancellative sites, compute these shifts. And this is a commutative diagram, as was proven by Lawson and Steinberg. And this is the picture we have one categorically. Also, bicategorically, Darien and Doret proved that adding suitable, in here it's just natural transformations, but what is it here? It's called, they call gamma transformations, but adding suitable two cells, they prove that this G and C can be standard to bifunctors which actually form a biequivalence. So these two categorically are biequivalent. And when you plug in the topology, they also prove that now this diagram still commutes, but now shifts is the bifunctor, the pseudo functor actually that extends taking shifts at the level of objects. So we have these nice pictures, but the question is, does this picture that we have allow me to recover étendues still as bicategories of fractions, suitable ones? Because in there, we would have a complete nice description of étendues, not only at the level of objects, but we would have the geometric morphisms are spans of morphisms coming from these two places, and the natural transformations are constructed accordingly to this theory of bicategories of fractions. And the first approach to this would be, okay, we know this is true for Grothendieck topoi. We know that Grothendieck sites, when we invert certain type of morphisms that will show up in a little bit, bicategorically, we obtain a biequivalence with the category of Grothendieck topoi. And so our most natural candidate, and here we are using Grothendieck sites, would be to take this WG to be just this family, but restricted to domains and codomains being left cancellative sites. The problem we have here is that this cospan that represents a geometric morphism in this picture of Grothendieck topoi in general may not have a top, a cancellative, a left cancellative vertex. More technically written, if I have a geometric morphism between the sheaves, I put a G to say it's Grothendieck sites sheaves. So the sheaves of A to the sheaves of B, where my A and my B are left cancellative, I can use this by category of fractions representation to build a cospan to represent this. But the problem is this C that appears here may not be left cancellative. So our bicategory is too restrictive to allow for this. And so our efforts now is to try to find a good set, a good family of presentations that do allow for this from the starting point of these Eresman sites and left cancellative sites. So let me start with left cancellative sites. The first step we do to enlarge them is use the notion of locally monic maps that Koch and Moerdijk introduced for toposes, precisely in the work in which they proved that like left cancellative sites, that every étendue can be presented as a sheaves over a left cancellative Grothendieck site. And so we transport these to sites, from topoi to sites. And so we say that the Grothendieck site C, that in a Grothendieck site C, a morphism is locally monic if there exists a covering such that when we pre-compose with each element in that covering, we obtain a mono. So it is not monomorphic, but up to a covering it is. And so monic maps in particular are locally monic because I can take the trivial cover of A given by the identity and I obtain F itself, which is monic. And the proposition is that if we have a site in which each morphism is locally monic, then the sheaves will be an étendue still. And so we have such a diagram with left cancellative. Now we are living inside locally monics because left cancellative sites are in particular sites in which every map is locally monic. And so we have this commutative diagram. And now we transport again this notion of torsion-free object that Koch and Moerdijk introduced in that very same paper. And so given a Grothendieck site, we say that an object is torsion-free if every morphism that lands on it is locally monic. And so we say that the site then is generated by torsion-free object if for every object we can find a covering by torsion-free objects. Okay. And so if all morphisms in a site are locally monic, in particular, all objects are torsion-free. So our sites with only locally monic maps in particular are generated by torsion-free. And the proposition is, if I take such a site generated by torsion-free objects, then the sheaves are still an étendue. So we have this picture, left cancellative, locally monic, now torsion-free generated, and this all commutes. Very well. And now this family will be enough for our purposes. And for that, let me, what I said before, these LC maps that I mentioned before, let me now introduce them. A morphism between Grothendieck sites, so it's a morphism which is covering, preserving, and covering flat, is called the LC, Lemme de comparaison morphism, coming from this result in SGA. If and only if, I will be a bit vague here. F is essentially surjective after coverings in the codomain, namely that every element in the codomain can be covered. We can find a covering by elements coming from A. And then fully faithful up to coverings, basically morphisms. A morphism may not be sent to a unique one, but up to covering it is, and all the reasonings are more or less the same, but I won't enter into the details. And so this class is the one we will use. And so the class of LC morphisms in this two category of torsion-free generated sites admits a left calculus of fractions. And the theorem says that now the pseudo functor from sheaves, taking sheaves from this torsion-free generated to étendues, sends these LC morphisms to equivalences and actually induces a biequivalence like this when we are taking the bicategory of fractions that inverts these maps. So we have solved the problem on one side of the story, which just consisting on enlarging the category. But what happens on the other side of the story? Because if you remember, the relation was not that straightforward between the two. At the level of functors, it was not even an equivalence. It became a biequivalence at the level of two functors between left cancellative and Ehresmann. So let's see what we can do on the other side of the story. And for doing this, remember we had these ordered groupoids to define Ehresmann sites. And we are going to consider, instead of ordered groupoids, ordered categories. So we take a category internal to pose sets. So the same picture as above, objects are the objects in page 0. Vertically, I put the partial order in page 0. The order in P1 gives me the two cells, which are precisely the horizontal arrows, I mean the order between the horizontal arrows. But now my horizontal arrows may not be isomorphisms because we have a category and not a groupoid anymore. And now this same condition that we want to keep, it's now codified in this sentence. Domain is a discrete vibration. Now we have to add discrete because before us we had isomorphisms horizontally, vibration was enough to guarantee this. Now we need a discrete vibration. So let's start with this. Now what we're doing in the Grothendieck part of the story, we allowed for more morphisms than the monics. So in here what we're allowing is, okay, we have the monics if you want kind of vertically, and we are allowing for other things horizontally that may not be just isos. So it's a little bit the intuition behind. So the two different are indeed horizontal. We don't have isos anymore. And this is a discrete vibration. And given such an ordered category, we want to put topological information on it. On the vertical direction, we know what to do. We had our Ehresmann topologies before. But now we want some information on the horizontal direction. What is covering in that direction, what is not. And that should be compatible in a certain way with a vertical one. And what we want is that every arrow, now it's not an iso, but it is close enough. We want them to be covering, every single arrow to be covering in a certain way. And so how we codify this idea is as follows. We take what we call horizontal quadrability, and this for every diagram of two horizontal arrows we can find is an OR condition, right? We can find the diagram like this, which is commutative. We impose that every horizontal arrow is a horizontal regular epi. And this is, if you realize, is just giving an atomic subcanonical coverage. So this is basically what we are going to consider covering. If we have this information, every arrow covers. It implies every covering sieve, which is not empty, will be covering. And this is just the atomic site, which is, and the horizontal regular epi guarantees that this is subcanonical. And then we add the compatibility with the vertical direction. And it is that for any diagram like this, there exists a horizontal arrow and a 2-cell filling the diagram. And why do I say also that this regular epi is given compatibility with the vertical direction? Basically because we don't want monics to appear horizontally. We want them all codified by the vertical arrows. So horizontally, if we have a monic, because it's a regular epi, it will be immediately an iso. So we don't have non-trivial monics if you want horizontally. And we define a generalized Ehresmann site, an order category with a vertical Ehresmann topology, and these 3 conditions on the horizontal arrows. And we have added a lot of information, but maybe too much that may not guarantee the behavior, étendue-like behavior that one would expect. So we translate locally monic and torsion-free generated to the setup. And basically locally monic is an arrow horizontally is locally monic if and only if I can find the vertical covering such that the unique 2-cell I fill in with, so the restrictions are isos. So we only remain with the vertical direction. And an object is torsion-free if every horizontal morphism landing on it is locally monic. And so we can define as before a torsion-free generated generalized Ehresmann site if every morphism can be covered first vertically and then horizontally, and the domain of that is torsion-free. So we have first vertically over A and then one arrow horizontally on top of AI. Okay, so this allows us as before, we define pre-sheaves. We can define sheaves, which they have to be sheaves for the vertical part, and then we have to impose the sheaf condition for the horizontal part, which is basically every element now is a single arrow, so every element is self-compatible. Every element that is self-compatible in f of A must become for a unique element in f of B, where self-compatibility is written like here, but it's not a complicated condition. Yes, basically now we are always thinking of our arrows being decomposed as horizontal, vertical. And what we are claiming is that for every 2 arrows that are over A and that compose nicely over F, meaning that their composition with F is the same, which is this condition here, then they go to the same object. So this is a self-compatible object, and it comes from a unique, we have to check that it comes from a unique element in f of B for this to be a sheaf. So we have our definition, and then what we prove is with such a site, torsion-free generated generalized Ehresmann site, we can associate a torsion-free generated Grothendieck site such that they have the same sheaves. Description very briefly, the objects are the same. So I have my Ehresmann site, I assign the same objects. The morphisms are just formal compositions, as it was kind of already implied by the definitions we have put. And the topology is basically this family of formal compositions covers if and only if the vertical part covered. Okay. And the corollary is if Pj is such a torsion-free Ehresmann site, then the sheaves are an étendue because we knew it for TFG generated, torsion-free generated Grothendieck sites. And these two are equivalent. These sheaf categories are equivalent. So therefore, this sheaf category of an Ehresmann site is an étendue. And the good thing is we have a reverse way. So for every torsion-free generated Grothendieck site, we can associate a torsion-free generated generalized Ehresmann site with the same category of sheaves. Before, this was an ISO, this is an equivalence. It's not an ISO anymore, but no problems. The construction is a little bit more tricky. I will be a little bit vague in here, but basically we have our Grothendieck site. We can find an LC morphism, so that guarantees that the sheaves will be the same. Where our guy is bigger and it has these nice properties. It's torsion-free generated still, but it has all my finite limits, and it has a regular epi-mono stable orthogonal factorization system. We can do this, and from this G bar, T bar, we can build our Ehresmann site. The objects are the sub-objects in G, so equivalent classes of monos. The two cells, basically up to taking a good representative, basically the vertical arrows is inclusions of sub-objects. The horizontal arrows are just regular epis, and this writing it with the correct, I mean, up to, you have to check that it doesn't depend on the covering. These are just commutative diagrams. And then we can put the topology as well. Two monics, I mean, a family of monics inside, in this sense, of another monic map, its equivalent class, is covering, if and only if the associated morphisms from the AI to the A prime cover in the topology we already had. And now the corollary is, okay, if I have an étendue, I can, and I know I can present it as sheaves over a torsion-free generated Grothendieck site. And now with this construction, I see that this is sheaves also over certain Ehresmann site. So these Ehresmann sites we found present nicely at the level of objects our étendues. And this is what I wrote down here. If P is a torsion-free generated Ehresmann site, the sheaves are étendues, and any étendue can be recovered in such a way. And the question comes now, what bicategorically? And that's what we're busy right now with. And so what we know is if I take this torsion-free generated Grothendieck sites with these nice properties that we found, then if we invert LC morphisms there, we do recover étendues. And now the story is, we think, but it's still work in progress. We have to define properly what are two morphisms here, what are one morphisms here, and we're checking all the comparisons. This takes a lot of time, but we are pretty certain that something of this sort will be true. And this is that these two guys are bioequivalent, so which immediately allows us to transport these LC maps from one to the other and obtain also our bicategory of fractions as we wanted. And with this, I just want to thank you for your attention, and here a list of references I've been mentioning along the way.
Okay, thank you, Julia, for your presentation. And we have our usual round of silent applause. And now we move to question time. So whomever wants to ask a question can unmute themselves and ask the question. So while people think, I will ask a question. So I wanted to ask, so once this will be done, do you have like future ideas on, like, do you have some applications of which you would like to apply this, or this is some kind of, we wanted to clarify the global picture?
We wanted to clarify the global picture. What remains undone also after this is the relation with the Tal groupoids, and see if we can link all the presentations without jumping to the sheaf level, which would be very nice if you can switch between the different ways of watching at this story. And that was basically our most important motivation, was first the global picture, and then try to understand, like give a full understanding, bicategorical understanding of presenting étendues, if you want. Yeah.
Okay, thank you. Enrico has a question, and also Josh. Maybe let's start with Enrico.
Yeah.
Who raised the question first, the hand first, and then Josh.
Thank you, Julia. Is it possible, or it is very complicated, to give an idea of why at the moment you ask that the domain of the groupoid is a fibration, and even more later you ask that it is a discrete fibration. So what is the meaning, not the technical meaning, but why it is assumptions?
In the ordered groupoid, so the first time like Lawson and Steinberg worked on this, they didn't use this double categorical perspective on it. And so they give the definition of ordered groupoid this way. And so you can encode this domain, I mean, their properties, you can encode them with this vibration property. So at that point, I don't know what their intuition was. At this point, after we have worked a lot in this project, in a certain way, we seem to be heading to, we want a factorization system in our site. And so the uniqueness of the composition, if you want, of an arrow as a monic and whatever we want covering, if you want, on top, will be given by this vibration. So you want a unique way of filling these two cells. And that's somehow the thing that we're a little bit also behind the enlargement on the purely Grothendieck side of the story is we want to allow more morphisms, but in the way everything restricts in the end to having monics and something above, if you want, and that we can nicely factorize things in a unique way. So this enlargement that we do to go from Grothendieck to these double categories now, that I take this LC map to a G bar up here. I don't know, it's very here, yeah, in the first step. What it basically does is I take my site, I take the essential image in sheaves. So basically I go Joned and then I sheafify. And in there, I complete under finite limits and then I take set objects. So basically we are really taking the factorization system of the topos in epimonic, and we impose it on our site. And this allows us to write nicely morphisms as a composition of horizontal vertical. So this vibration property in the end is what you want to guarantee is that this way of seeing your morphism is unique, coming from the Grothendieck picture.
Thank you.
Thank you, Enrico. Now, Josh.
Yes, thank you for the talk. I'm curious about these two cells. So in the site theoretic case, it's very obvious,
yeah,
like what the two cells should be between the sites. When you're talking about extending this to groupoids as well, what will the two cells look like on the groupoid side?
This is described in Darien and Doret's paper. They're called gamma transformations, and somehow it's like you have like you divide the transformation like in a horizontal and a vertical part in a nice way. I mean, right now I don't have in the top of my head because at the level of the two categories is them who work more into it, but it is really thinking of as you had in the morphisms, you have like transformations that have like a horizontal, if you want, part transformation into the and then a vertical part that combine nicely. And so they are called gamma, like capital gamma transformations. Yeah.
Okay, so these are two cells between you're still considering the morphisms of groupoids as homomorphisms of groupoids rather than bispacers.
Yeah.
Okay.
So indeed, no, but in here, because you have, there's one thing there. So they are morphisms of groupoids, but you have the topological information. So on the Grothendieck part, you have this covering flat, covering preserving, and you have to make sense of this on the Ehresmann side. So we have what is covering preserving is nice. Basically, you take your functor and it sends coverings to coverings, but the covering flatness condition, it's technical to you have to make so we define what horizontal vertical cones are, and then you have to see that things work as in the Grothendieck side way, but in which you have to deal with horizontal and vertical information at the same time. But then you take indeed functors that preserve my vertical coverings, if you want, and such that have this flatness, which is written in terms of HV cones, which in the end, when you see it written, make complete sense, but it takes a little bit of work to figure out what the correct notion should be.
Okay, cool. Thank you very much.
You're welcome.
Okay, so do we have other questions from the audience? Okay, so if we don't, thank you, Julia, for this presentation.
No, thank you.
And now we move to the last